Hi class, I hope you're doing well. Welcome to the second half of today's lecture. So in this part of the lecture, we're going to talk about the real kind of obstacles to trying to look for and trying to communicate with intelligence off of Earth. Okay, so in the background here is a message in a bottle. And that's because one of the points in our discussion today, we're going to talk about one of the first attempts to communicate with life off of the Earth, which is namely through the use of artifacts, which in this case are spacecraft that we've sent out from Earth. So in this case, spacecraft very much are artifacts that will travel through the cosmos. And if a alien species should stumble on them at some point, then we wanted them to know something about who had built the spacecraft. And so in this way, it's very similar to this message in a bottle idea for those of you who ever participate in this. Okay, so that's the theme for today. So let's take a look at some slides and we'll talk a bit more about this. So the first, the cover slide here is a picture of New Horizons. So those of you who have been paying attention to astronomy for the last couple of years will know that New Horizons was the first and only spacecraft so far to have flown past Pluto. It is one of the 5 fastest spacecraft leaving the solar system right now. It does not carry a message of the sort that we're going to talk about today on it, but it is a human artifact that could be lost into the wide universe and possibly found at some point in the future. Okay? So let's talk about what the challenges are. So we're going to talk about the big problem, and the too long didn't read version of that is distance. Distance is always the problem in astronomy, as you have probably learned by now. We'll talk about the problem of capturing the attention of alien species, and I'll tell you a story about the LGM, which is something that captured our attention, and then we'll end with this discussion of artifacts and communication. Okay? So this was our list of challenges. So this half of the lecture, we're going to focus on this. It's late. I'm sorry. Focus on this part of the discussion. Okay, what kinds of format might communications take, and what should we think about, and how hard is that information conveyance? We'll come back to both of these topics again. They're both very big topics, and they take a lot of discussion. But we'll come back to them next week and talk about them in a slightly different context as well. Okay, so distance is really the problem. And so there are basically 2 modes of communication to deal with the distance problem. One is the road trip, or the message in a bottle. Both of those are functionally equivalent, and the telephone call. Okay, and both of these methods, you should walk away from this lecture recognizing that both methods, no matter which one you use, they're both subject to the problem of the enormous distances that we're talking about. They're hard to use as a modicum for communication, which is why the issue of finding extraterrestrial intelligence and communicating with extraterrestrial intelligence is so hard. Okay, but as we will see, we're all optimists, and that should never discourage us, right? Right. Okay, so let's talk about the enormous distances here. So we have our 2 favorite stars. These are the Sun, the closest star to Earth, and Proxima Centauri, which is the closest star to our Sun. And as it turns out, it's the closest star, which happens to have an exoplanet around it. Okay, Proxima Centauri B, which we've already talked about. So let's imagine that we're going to do the road trip model. Okay, so you and I have talked about this before. The road trip model is we get in our Yugo and we drive at the kind of average speeds that we as humans can normally encounter. Let's say 60 miles per hour. That's pretty fast for a Yugo, but let's go for it. Traveling at ordinary human speeds, how long will it take us to get from the Sun to Proxima Centauri? A long time, 48 million years. Okay, so that's longer than humans have been on planet Earth. Okay, so it's a super long road trip, never going to work at normal human speeds. Okay, but you should be going, yeah, but Larson, come on. Yugos are really slow. They only go 60 miles per hour. What if we send something faster? Okay, well, the fastest thing ever built by humans is the Voyager 1 spacecraft. It is currently traveling at 38,000 miles per hour, 16 kilometers per second. Okay, so traveling at 38,000 miles per hour, it would still take 75,900 years to get to Proxima Centauri. So humans have certainly been on Earth for 76,000 years, but that is longer than recorded human history, almost 14, 15 times longer than recorded human history. Okay? So even the fastest that humans can go, getting to the nearest star is really, really hard. And so by and large, we don't really think about the road trip model. Okay, that's not entirely true. The very last day of class, we'll talk about starship travel, and we'll talk about ideas we have to deal with this problem that we're talking about right here. The solution is to go faster, obviously, but we'll talk about what the prospects for that are at the end of this class this quarter. Okay, so really what we're confining ourselves to is the idea of sending radio signals. Okay, so I've illustrated that here as a cell phone. You know, we often talk about this euphemistically as talking on the phone with our extraterrestrial intelligence friends, but what we really mean is radio telescope, but it's the same technology. Can I send a radio signal from one place in the cosmos to the other, have someone intercept that radio signal, interpret it, and send me one back? Can we build an interstellar walkie-talkie? Okay, so radio signals are a form of light. They travel at the speed of light, which is 186,000 miles per second, or 3 × 10⁸ meters per second if you're using metric, which we really should be. But even traveling at the speed of light, it takes 4.3 years to make the journey from the sun to the nearest star, not just to any star, to the nearest star. And so if by some miracle there was intelligent life on Proxima Centauri B, then they would have to interpret the signal and send a message back. The soonest that we could expect an answer is more than 9.5 years after we send the first signal out. Okay, so to illustrate why that's kind of a bit of a problem is think about what were you doing 9.5 years ago? Do you remember? Okay, and do you remember what you cared about? Do you care about the same things now that you cared about 9.5 years ago? Well, most of you were young, right? You were probably in middle school then. And so you might say, of course not, I'm a grown-up now. But let me tell you, I'm a grown-up, and I was still a grown-up 9.5 years ago. Okay, I was about where you all are. I was in graduate school, and I don't care about the same things now that I cared 9.5 years ago. Okay, so people change. And this is going to be an ongoing part of the story, is that when we send messages out into the cosmos, the receipt time, the time it takes the message to go out and then come back, is so long that the answers we get back may not necessarily be of interest anymore. It depends on what we're trying to communicate. Okay? And that's a topic that we'll come back to over and over again. So to drive this point home, this example here is just for Proxima Centauri, which is 4.3 light years away. If I look at the nearest exoplanets, and so I went to the exoplanet catalog and I just took all the nearest exoplanets and I threw out all of them that weren't habitable. I kept all the ones that were in the habitable zone of their star. This is the list that would fit on one slide in the lecture. Okay, so it's what, 10 or 11 stars. Okay, they're all within, so the farthest one there's about 24 light years away. Some of them are on planets similar to Earth. Some of them have crushing gravity compared to the Earth. All of them are in really short orbits, okay, except for that one there around Tau Ceti, although it has really super strong gravity. And so, you know, these are worlds that live in the habitable zone, but they're not necessarily worlds that you and I might survive on. But why does that matter? Maybe life there is well attuned to surviving in strong gravity. Okay, so these are the potential candidates. But if you look at those distances, that's the key. The distance away times 2 is how long it takes to send the signal and get an answer back. So with the exception of Proxima Centauri, nowhere on this list is closer than 20 years round trip light time. And so we're going to carry on a conversation. You can send a text message, 20 years later, you'll get the next text message. You send another one, 20 years, you'll get another one. If you live to be 100 years old and you sent the first text message, your parents sent it for you the day you were born, there will only be 5 total exchanges. Okay, so go get your phone right now and look at the last 5 text messages you sent and what their content was, and think hard about what it takes to make an intelligent set of messages in a conversation. Okay, it's hard. And deciding what to say and what's interesting to say and what's important to say is another part of the complexity of the problem of trying to communicate with extraterrestrial intelligences. It's both a problem in terms of what might we want to say, but it's also a problem in terms of interpretation. If we receive a signal from the stars and we have to decide what's in it, one of the questions we have to ask ourselves in order to help with the decipherment is, what did some alien civilization think was important to send in a message out to the stars? Okay, so intent is important. And so this kind of illustrates why being very diligent about clear on what your intent is crucial, because the round trip times are really, really long. Okay? Now, the round trip times are certainly a problem, but if you send a message out there, presumably you're hoping someone receives it. And you're hoping that they also send an answer back, okay? But the hoping they receive it is really the first problem you encounter, okay? Because you want them to notice the message. You want them to realize it's a message. You want them to realize, hey, we're out here trying to send you a message. Pay attention. Try and figure out what we're telling us and send us back your favorite recipes for cookies or whatever it is we ask them. Okay, so getting the attention of an alien civilization is really hard. Okay, so to illustrate that, let's imagine what alien civilizations might have detected from Earth if we had sent out the brightest signal that we could have sent. Okay, so the brightest sources of light on Earth are going to be subject to the 1/r² law that we talked about. The light's going to get dimmer the farther from Earth it gets, which is going to make it harder and harder to detect. Okay, and we'll come back to this when we talk about radio signals in a couple of lectures. But let's just talk about ordinary light. So the brightest light that humans have made is with this laser on the left. Okay, that's the NOVA laser. It produced about 16 terawatts of power. Okay, so that's 1.6 times 10 to the 13 watts. There's a new laser being built, which will produce, I think, 500 terawatts. Okay, that's called the National Ignition Facility. These lasers aren't being used to communicate with outer space. These lasers are being built to try and attempt to develop nuclear fusion into a power source. Okay, but when we talk about starship travel, we'll come back to the discussion of big lasers, which is why I want you to know about it now. The largest, most energetic event humans have ever created is this nuclear bomb test called the Tsar Bomba. This was carried out by the Soviets in October of 1961. It was a 420 petawatt nuclear explosion. It was the largest nuclear explosions ever carried out by humans. Okay, it was many hundreds of times larger than the Hiroshima atomic bomb. Okay, so in terms of watts, that's 4.2 times 10 to the 17 watts. So that's the brightest light that humans have ever produced. Okay, so imagine that all of that light just went out into the universe and some aliens had something the equivalent of the Hubble Space Telescope. Okay, so the Hubble Space Telescope's arguably the current most powerful telescope we have. It can see the faintest things, see the things the most farthest away of any telescope humans have ever built. So how far away could the nuclear explosion from the Tsar bomb be seen by aliens who had a Hubble Space Telescope at their disposal? Okay, well, if you do that calculation, if Hubble was looking at the exact moment of the explosion, it could only see that explosion from 120 light years away. That is really not very far out into the galaxy. If we look in the solar neighborhood, the total number of stars in the solar neighborhood is only about 6,000 stars. Okay, but the Milky Way has 400 billion stars in it. Okay, so getting attention of an alien civilization is really not going to be easy, because even making the biggest, brightest signal we can imagine seeing, it's only going to go so far out into the cosmos. Okay, so this idea is not a new one. This is related to something called optical SETI, the search for optical signals from extraterrestrial civilizations, and we'll come back and talk about that a little bit in a future lecture. Okay. Now, the real problem with looking for signals from aliens trying to get your attention is that the universe is always trying to get our attention at the same time. Okay, so the example of that, so we were talking here about these nuclear explosions, the example of that is something called gamma ray bursts. So gamma ray bursts were actually discovered by the military in 1967 because they had put into orbit a set of satellites called the Vela satellites that were designed to look for nuclear explosions. They were trying to guarantee that the Soviets, and the Soviets presumably were doing the same thing to us, were obeying the nuclear test ban treaty that had been put in place in 1963. Okay, so they were satellites designed to detect nuclear explosions, just like that Tsar Bomba. Well, the military freaked out because the first satellite they put up, they detected a nuclear explosion. And then they started detecting them every couple of days. Okay, and so eventually they figured out, nope, can't be the Soviets. There's no way they are putting a bomb on the table and blowing them up every couple of days. Okay, they eventually figured out that these things were coming from outer space. Okay, they didn't know where, they didn't know how. All they cared was that it wasn't coming from the Soviets. Okay, so it took them almost 10 years, but in 1973, they finally declassified the existence of the gamma ray bursts and let the astronomical community know, hey, there's these big explosions. They're from outer space. We don't know what they are. Have fun. Okay, and so astronomers began investigating. That meant they began trying to detect them themselves. We eventually flew many satellites for doing this. They began trying to figure out what might cause them. And in particular, we had to know where they were coming from. And it took from 1973 until 1997 before we finally figured out that they weren't coming from the Milky Way galaxy at all. Okay, so these are extragalactic sources. They're coming from way far out in the universe. There are mechanisms that are still not fully understood. Some of them are caused by neutron stars colliding. Those of you who have been paying attention to astronomy know that this is a source of gravitational waves. They also produce one of the forms of gamma ray bursts we see. The other form of gamma ray bursts we think are a form of super energetic supernova. Okay, and we could talk about that at great length, but they are not the signatures of alien civilizations trying to get our attention. But they look like exactly the sort of thing you might imagine you would try and do, produce a big explosive light if you're trying to get the attention of an alien species. Okay? Now there's another mechanism you could use to try and get attention, which is you could repeat a signal. You could just send the same signal over and over and over again. Okay, well, such a signal was discovered. So again, in 1967, Jocelyn Bell, so this is a picture of her when she was a graduate student, when she made this discovery, she discovered a fixed radio source. That means it was a radio signal at the same place in the sky. It was in the constellation of Aquila, okay, that emitted a repeating detectable radio signal, the same signal over and over and over and over and over again. So you can see down here in the lower left, this is her plot of her data. And you can see in that middle row, there's a flat line and then there's a blip. And then you move over 2 squares and there's a blip. And you move over 2 squares and there's a blip. And you move, that's the repeating signal over and over and over again. So it was so regular. It was just right smack at the same time, over and over and over again. And staring at this, you have to say, oh my gosh, what is causing these repeated radio signals so quickly? Is it some kind of lighthouse? Is it something trying to get our attention? And they didn't know. They'd never seen a signal like this before, ever at all. And so they called it LGM-1. Okay, and LGM, as you might guess, stands for Little Green Men. Okay, it really does look like exactly the sort of thing you might try and send out if you were trying to attract attention. Okay, well, it took a little while. It took about a year, but eventually we figured out this is a natural phenomenon. Now today we know of something like 2,000 of these. Tommy Gold and Franco Pacini worked it out, and they proposed that it was a rotating neutron star. So a neutron star, as we've discussed a couple of times in the past, is a dead star. It forms when a star explodes. It's the skeleton that's left behind. And it can have that bright flashlight beam coming out of one of its sides. And as that beam sweeps across your line of sight, it makes that pulsing radio signal each time it rotates, just like a lighthouse rotating. It's not a constructed lighthouse. It's a natural lighthouse. And so this is the problem. Nature can fool us with things that are really happening. Okay, so this today is what we call the pulsar. This particular pulsar is called 1919 plus 21. Okay, now I couldn't find a recording of this pulsar, but I did find a recording of the radio data of the crab pulsar turned into sound. And I want you to listen to it because in a couple days, we're going to play a sound of a signal that's meant to be received and interpreted as an intelligent signal. So I want you to hear what a real pulsar sounds like first. Okay, so this is what the crab pulsar sounds like. Okay, so the crab rotates about 3 times a second, so it's rotating very fast, but it has that kind of repetitious signal that all pulsars have. Okay, so keep that in mind. We'll come back to that when we talk about signals receiving signals from the universe in a couple of lectures. So let's jump to the message in a bottle question. So that's really the last part of this, and in the form of our spacecraft, we really have sent artifacts out that are definitely on their way out of the solar system. They will be lost to humanity forever. They will be drifting among the stars, and given enough time, they will pass near other stars in the Milky Way galaxy. Okay, so the first 2 spacecraft to leave the solar system or to be sent out of the solar system were Pioneer 10 and 11 in the 1970s. So these made the first close passes of Jupiter and Saturn. Pioneer 10 is traveling at 26,720 miles per hour, generally in the direction of the star Aldebaran, which is in the constellation Taurus. It will pass close to Aldebaran, close meaning within a light year or so, in about 2 million years. Okay, so Pioneer is heading out, but it's going to be in deep space and ultimately lost, and unlikely anyone will ever find it. Okay, but don't let that discourage you, as we'll discuss in a moment. Pioneer 11 is traveling a little bit slower, 25,150 miles per hour. It's going to pass closest to a K-dwarf star called Tycho 9921921, and that will happen about 928,000 years in the future. Okay, so about half the time that it's going to take Pioneer 10 to get anywhere interesting, Pioneer 11 will get somewhere interesting. Okay, but still, you can see the immense travel times are a problem there. Okay. They travel very, very slow. So why are the Pioneer spacecraft messages in a bottle? So the Pioneer spacecraft were the very first spacecraft to carry a message specifically intended for the possibility that they might be discovered by an alien intelligence. Okay, and so that message is in the form of the Pioneer plaque. It's the same plaque on each of the 2 spacecraft, and if you look at pictures of the Pioneer spacecraft, you will see it bolted on the side of the spacecraft. It's engraved in gold. Gold is a very non-reactive metal, and so it should survive for millions of years in interstellar space. And so what you see here is a combination of many, many things. It looks like just a piece of abstract art, but if you recognize that it's designed to be interpreted and communicate some information, and you recognize or know, and we'll come back to this message over and over again, that the message is being described in a language that should be interpretable by a technologically capable civilization, then we hope that the way we've laid it out will make it possible for a species capable of building radio telescopes to decipher what's written. Okay, so what's on the plaque? So this is the key right here. This is a representation of molecular hydrogen, H2. Okay, molecular hydrogen is the most common substance in the galaxy. It's the most common neutral gas in the galaxy, and it emits a very specific radio frequency, what we call the 21 centimeter line. So the 21 centimeter line of hydrogen is the primary atomic line that we use to observe the universe in radio. And so the assumption is that if an intelligent species can build radio telescopes, they probably used it to do astronomy just like we have, and they're well aware of hydrogen and the wavelength that 21 centimeters represents. It's a physical quantity that we're communicating by drawing a picture of the hydrogen atom, okay? Now you'll see there underneath the bar, there's the little numeral 1 written, okay? And so this is an indicator that throughout this diagram, you'll see the separation of hydrogens written and ones written, and those are ways of representing numbers throughout this entire diagram, okay? This is a pulsar map designed that if you can recognize the pulsars, and each of the lines represents a specific pulsar, and written along the line is the distance from Earth to that pulsar and the radio frequency of that pulsar. That is how fast it's spinning. And with enough pulsars, if you can find these pulsars in the galaxy, you can triangulate and work your way back and figure out where this Pioneer spacecraft came from, namely the sun. Okay? So here is a map of the solar system. You can see the Pioneer spacecraft, an arrow showing that it originates from the third planet in the solar system. Near the planet, you'll see little numerical indicators. They're basically telling you the separation of each of the planets from the sun. You'll see Pluto is still included in this list. So the recognition of the number of planets may be a little bit dodgy, because who knows what aliens think you identify planets are. But Saturn is very prominently ringed, and the inner solar system is very clearly laid out in the way that it is now. Okay, so this is all designed to be information that can help any intelligent species that might encounter the Pioneers to work their way back to where they might have come from. Okay. Now, on the upper right and the center is a picture of the Pioneer spacecraft, and to scale the two human figures, you'll notice some numbers over there that basically give you the size of the human figures, which in turn gives you the size of the spacecraft. As you might imagine, the human figures are the most controversial issue surrounding the plaque. There certainly are objections from people around that were made at the time the plaque was designed and sent out because the figures are nude. But the argument was made that we wanted to represent humans' physiological forms, and in a way that was not indicative of a particular culture on Earth. We wanted to show the species as it were, and so this is the way that it was depicted. Okay. So this was the first message in a bottle that we've sent. It's on the two Pioneer spacecraft, and it will far outlive our civilization as the spacecraft travel out into the universe. Voyager 1 and 2 are the fastest spacecraft built in human history, and they are our second examples of messages in a bottle. Voyager 1 is traveling at 34,370 miles per hour. It is the fastest spacecraft in history. It is heading generally in the direction of the star Gliese 445, and it will travel at its closest point to that star in about 40,000 years. Voyager 2 is not that much slower, 34,000 miles per hour. It's traveling generally in the direction of Ross 248, and it will arrive near Ross 248, or at least pass as close to Ross 248 as it's going to get in 42,000 years. Okay, so the Voyagers carry records. Okay, so rather than plaques, they carry phonograph records. So there's a golden phonograph record. You can see it there at the top. It's an actual phonograph record. It's just made out of gold. Okay, the needle to play the phonograph record is enclosed on the spacecraft. And then the lower image here is the plaque that covers the spacecraft. Okay, so once again, on the lower half of the plaque, you'll see the hydrogen with the indicator of the 21 centimeter line transition. You'll see the pulsar map locating Earth. In the upper left of the cover, you'll see the phonograph needle and then a circle with numbers written around the edges. This is basically a description of how to play back the data from the record. You put the needle on the record, and as it goes around, it releases encoded data. Okay, and then on the right, upper right there, you'll see what the data looks like as it gets read off the needle. Okay, again, indicating what ones and zeros binary data looks like. It shows how to, the two squares there show how to take the data and construct images. And then the circle in the square is the very first image that's on the record. Okay, so the record contains 115 images of Earth. Okay, variety of images, pictures of the landscape, pictures of the life forms, pictures of buildings, pictures of our civilizations, all kinds of images. We'll talk about that in a minute. It also includes audio greetings in 55 different languages, and it includes 90 minutes of music. Okay, so the Earth's greatest hits, as it were. So there's some Mozart on there, there's some Bach on there, there's a Navajo night chant on there, There's some panpipes from the Solomon Islands. There's a Peruvian wedding dance. There's some traditional Aboriginal songs from Australia. There's some blues guitar from Blind Willie Johnson, who's one of the most famous blues guitarists from the early 20th century. And the only rock and roll piece on there is Johnny Be Good by Chuck Berry. Okay, those of you who are Saturday Night Live fans, you'll know there's a famous Steve Martin skit where he plays an alien who's found Voyager, and his only message for Earth is send more Chuck Berry, right? So, but it's the only rock and roll on the record. But there's 90 minutes of music from Earth on the record. There's an additional record message on the record, which you can kind of see in images of it. It's scratched around the inner edge of the record there, right over the center part where it says the sounds of Earth. It's a handwritten message in English that says, to the makers of music, all worlds, all times. Okay, so if you're interested in the Voyager record, you can see it. There are many public sites, so goldenrecord.org is one example. NASA's site there is at the Jet Propulsion Laboratory at the Voyager pages, so you can go read about all the music, see pictures of all the images. But if you'd like your own copy of the record, so an actual phonograph record that you can play, you can get CDs with the images and books that tell you all about it. Ozma Records was a Kickstarter a couple years ago that put these things into production, and you can still order them as well. Okay? If you can find it, it's now out of print, but Carl Sagan, Frank Drake, Ann Druyan, Tim Ferriss, John Lomberg, and Linda Sagan, who worked on the record, wrote a book about it. It's called Murmurs of Earth. So you can still find it. It's in out-of-print bookstores. It's a very nice book. And for those of you who are music fans, one of my favorite folk artists is an artist named Mary Fall. Mary wrote a song several years ago on an album called Everything's Gonna Be All Right. And that song is about what's on the Voyager record. And so it's kind of a cool song to listen to. Okay, so let me show you. So I have here my copy of Murmurs of Earth. So this is what the Murmurs of Earth book looks like. Okay, it's a nice book because it has, as you can see here, all the pictures that are in the Voyager record, but it also contains an explanation of what the picture is and why they picked it. Okay, as well as discussions of picking the music and those sorts of things. When the book was originally released, it had copies of all the music and images with it on a CD, but used copies almost never have that. This is a book of the Voyager record that you can get from Ozma, okay? And so this particular one has CDs on the back with the music and the images. And so it also has copies of what all the pictures from the Voyager record look like, but it doesn't have the cool explanations in it that the Murmurs from Earth book has. Okay, so those are examples of how you can get access to it. You can certainly still find it all online, but for those of you who like tactile stuff, books are certainly the way to go. Oh, and I'm wearing my Voyager record shirt for you today for lecture as well. So, okay, so that's all I'm going to say for this half of the lecture. We'll come back and talk about what's called the Fermi paradox in Friday's lecture, and then next week we'll start talking in earnest about sending and receiving signals from outer space. Okay, so I hope you're all doing well. Take care of yourselves, and we'll talk again soon.